Here we go. All right, so hello YouTube, hello everybody. The reading, so again, the reading for today is from chapter 10. It's all of chapter 10, 10:1 through 10:3. And the reading for Wednesday, and this wounds me inside what I'm about to say, but I think at some point even I must face reality. Though I prefer, reality. I prefer to avoid reality whenever possible. But yeah, so it is a fact that here's a very important distinction to make between chapter 10 and chapter 11. So chapter 10 will be on the final. Oops. Not what I want to do. Chapter 10 will be on the final. Whoa, that was weird. And chapter 11, this wounds me because it's like the most useful chapter of the whole thing, but it's a bit too much. It's a bridge too far. So this will not be on the final. Okay, so I mean, it's really cool. It's the fast Fourier transform. It is one of the top 10 algorithms of the 20th century, and still going strong into the 21st. But it will not be in the final. So I can understand if maybe people want to sort of sit back and relax and soak it all in, because I think so. We'll start talking about that on Wednesday, and talk about that going through the last day of class. But if your attention is maybe not the most focused on it, I understand, because it's not going to be on the homework. Problem set 11, you'll see, is very short. So anyway, so problem set 10 is ostensibly due today. The outline for problem set 11 is due on Thursday, and problem set 11 itself is due on the last day of class in principle. But all deadlines are flexible, and I will be collecting, and I will take revisions and sort of completions up through the last day of finals. Work accepted through the end of finals, which I think is May 19th. I think it is. Anyway, so catch up as much as you can. So if you want to pursue any, so everybody should have received their graded exam 2s back last night sometime. Good job for the class overall, and especially during this insane time of quarantine and pandemic. Thank you very much for all the hard work you put in. I'm really impressed. Anyway, but the point is, if you want to improve your grade for whether you did awesome on the exam or less awesome, perhaps, the way to improve your grade from here on out is to and it's always the way to improve your grade is to sort of get those homeworks done, get as much of it done as you can, and especially because the final, which will sort of be taken along the same lines, will be based on all the homework that we've done in class the whole time. All right. So, oh yes, and then as always, we will have a problem session on Friday from 10:30 till noon. Okay. Anyway, any questions about mechanical stuff before we? There's a little bit of stuff to finish up from last time. I think mostly there's stuff that there's something I didn't finish so cleanly, so I'm going to try to do that, redeem myself by doing it again, and then we're going to talk about groups. So any questions before we begin? Okay, let's go. Okay, so where were we? Right, we were talking about the discrete Fourier transform, the DFT. So if you fix a positive integer capital N, and we let omega be the primitive nth root of unity, and actually let me just remind you of the picture of that. So somehow this is my favorite nth unity root of nth root of unity to draw. So if capital N equals 5, I guess because it looks kind of cool, it's like this little starfish. You can sort of break up the unit circle in the complex plane into fifths, and then that's omega. This is omega squared. This is omega cubed. This is omega to the fourth. Anyway, all right. So those so omega, the original one, is that's the sort of what's called the natural primitive nth root of unity. So we let f be a function from z mod n to the complex numbers, so that's a thing we call a signal. We define the discrete Fourier transform of that signal f to be f hat, which is another function. So this is sort of which I guess technically speaking is a function, but a signal. But we actually think of f hat as being a function on frequency space. We think of Z mod n also as a space of all frequencies, possible frequencies of fundamental sine waves on Z mod n, and anyway, whatever. We define f hat to be this formula here, the average of f of n times over all little n of f of n times omega to the minus nk, and we think of f hat of k as we think of that as being the spectrum of f. Because roughly speaking, as we're about to see, f hat of k measures the strength of the part of f that has frequency k. Sort of the what you might call the omega to the nk. The omega to the k part. Maybe omega to kx. Yeah. As we'll sort of see over here in this proof of the omega to the kx part. Okay, so that's the idea. But okay, as it is, it's a piece of math and it's a formula. And so let's see what we can do with the formula. So the next thing that we talked about last time is the inverse discrete Fourier transform, which is here you start off with a spectrum function f hat of k, and then we define the inverse discrete Fourier transform of f to be this thing here. It's basically, if you look over here, it's the same thing except with a sign change. So instead of taking omega to the minus nk over here, we have omega to the kn, and so with a sign change and also in different constant constant out front. And the whole point of the inverse discrete Fourier transform is that that you can undo the discrete Fourier transform. So that if you take f and you do the discrete Fourier, the DFT to it, and get an f hat, and then if you do that and then you do the inverse discrete Fourier transform, you recover f. And so there's 2 points of that. One is that the inverse discrete Fourier transform lives up to its name and actually inverts this discrete Fourier transform. And also, it's important to note, and the inverse discrete Fourier transform and the inverse DFT is computed almost the same way. So if you just happen to have in your back pocket some quick way of computing the discrete Fourier transform, then that quick way of computing the discrete Fourier transform will also compute the inverse discrete Fourier transform. All right, so this is just saying that the inverse discrete Fourier transform lives up to its name. And here's the part where we whip through the end, which is the proof of inversion. Which uses the following orthogonality lemma. So if you take a sum, if you fix a t, so again here we're thinking t is fixed. T is fixed, and and you sum over all possible k omega to the kt, then if t is 0, then you in that case, when t equals 0, what you get is you get the sum of like that sum of omega to the kt's is basically it's 1 plus 1 plus 1 n times, and that's why you get. Oh, I guess I'm kind of giving away the homework here a little bit. I'm sure you don't mind. So in that case, when t equals 0, then the sum of the kt's is going to be sum of n capital N1s. But otherwise, we get this cancellation. That's really remarkable. That if you sort of sum all these things together, you get 0. All right. So here's a proof of inversion. Right, and now for which we will need another page. Okay, so the point of the inversion theorem is that we take this formula and expand it, and hopefully we're gonna get and what we want to get is f of n in return. All right, so just so again, let's see if I can redeem myself. The way you do this is you switch the order of summation. So it's sort of like you have rows and columns. It's sort of like if you're adding up a bunch of numbers and rows and columns and rows, you can either add up over the rows first or add up over the columns first. And that fundamental fact means that we can here switch the order of summation. Sum as n, little n goes from 0 to capital N minus 1 of the sum. So we can add the k's first on the inside. And add the little n, sum over little n on the outside afterwards. And then remember, when you multiply two exponentials, this is the same as adding the exponents. So we get kx omega to the kx minus kn. And now that is going to be equal to, right, so that's, oh my gosh, there's a little bit of pre-calculus there. So this is laws of exponents. Well, I mean, it's not actually pre-calculus as you saw it, because secretly omega is a complex number, and you have to make sure that exponents make sense for complex numbers, and that but they do. And so the laws of exponents, kind of in some slightly more complicated way than I'm letting on here, actually work here. All right. So another thing we can do is we can bring out because this term over here, the fn term, is constant. So since we're summing over all k's, and f of n is constant with respect to k, then we can sort of drag that out front there, and get the sum as little n goes from 0 to capital N minus 1 of little f of n times the sum, or little k goes sum over the k's. And now I'm going to regroup this here. This is little k times x minus n. All right, and so now we have exactly what we have here in this orthogonality lemma that you're supposed to prove on your homework. I guess well, technically due today. Okay, but if you're behind, that I understand. That's okay. So this is sort of taking. So what we have here is we have this term over here, and we're taking here t equals x minus n. So so the point is, so remember x, so x is sort of, so x is a constant here. So remember, x is something that we held constant at the very, very beginning. X is constant. And we want to show that this is equal to f of x. So the point of that is all this stuff is supposed to come out to f of x. Like I said, we had it with it. We wrote the formula with an n over here, but same thing. It'll sort of work okay with an x. So remember, x is constant, and so this term over here, I guess I should put this in. So if you look at this term over here, so the only is capital N when t equals 0, when that is when 0 equals x minus n, and 0 otherwise. So this green thing, when you sum the outside sum over all possible little n, then the only time you actually get anything is when little n is equal to x. So the sum over all little n of all that stuff reduces to a single term, which happens when the n equals x term. And so, so long story short, this is an explanation for the following radical simplification. This is equal to 1 over n times just the stuff in here. So just the stuff in here that comes from taking little n equal to x, and so that is going to be f of x times, well, that sum when little n equals x, and we saw that we were just saying that when little n equals x, or in other words, when x0 equals x minus n, this sum is equal to capital N. So this is going to be equal to 1 over n capital N times f of x times capital N equals f of x. All right, so okay, so you don't need to know the details of that for the homework or the exams or whatever, but I think the takeaway from this, so yeah, so why did I do this, huh? Well, anyway, that we're done. That's what we wanted. The takeaway, this is something that happens all the time in this setting and many others. The takeaway, the executive summary, as they say, the takeaway is that the orthogonality means that sums will often, sort of double sums, often collapse. So we'll often simplify in this manner. All right, so I guess for this is not a proof class, and so if you just sort of store the thing, if you want to just sort of tuck one fact away in your brain somewhere in the back of your, if you want to tuck one fact away in your brain somewhere, it would be that the one fact would just be that when you have these sort of trigonometric sums, these sums of things involving powers of some omega, then often something like the orthogonality lemma, something like this, will mean that you'll be able to collapse a double sum like this into one term. Crazy. Okay. Anyway. Okay. Well, for what it's worth, I mean, like I said, it's not on the homework, but it's not on the exams, but it's still an interesting thing to sort of absorb the fact that the fact that you get this strange trigonometric cancellation. But for what it's worth, are there any questions about that? About the inversion theorem and its proof? Okay, so so here's the killer app. Sort of why is it that I mean if you're a musician, I guess I also end up using music as a motivation for this kind of thing. But if for example you're a musician, you might actually know some other applications of the discrete Fourier transform. But if you're just sort of a general person, a person in just generally interested in computers or mathematical computation, why should you care about the discrete Fourier transform? So the killer app is really that if you can speed up the discrete Fourier transform, then you can write a fast multiplication algorithm. And so let me remind you that remember how the multiplication of two polynomials. Let me draw a little picture of this. Remember how to when you draw the multiplication of two polynomials, x squared minus x plus 5, right? And then you like x squared plus x plus 7, and then you sort of get three terms over here, and three terms over here, and three terms over here. And so this is O of n squared. Remember that? I hope you vaguely remember that the standard multiplication algorithm for polynomials. Oops. The standard multiplication algorithm for polynomials takes time O of capital N squared, where capital N is the degree of your polynomial. I hope this picture kind of suggests jogs a memory as to why that's true. Remember we did that long ago, and I think I sort of said, well, this will come in handy at the end of the course where we really care about how fast this goes. All right, so I'm sure regular multiplication is like multiplication of numbers. Let me say, which is way more fundamental, is like this except more complicated. But we sort of use multiplication of polynomials as a simpler version of multiplication of of numbers. So, which is weird, right? I mean, it's just that when you multiply numbers, you have all this carrying, which is a giant pain to deal with. I mean, it ends up working out in the end, but it is kind of a pain. Anyway, so thanks to convolution, it is true that it is a fact, and this you can sort of take as a fact. If you can compute the discrete Fourier transform of a period n signal in a sort of less time than O of n squared, so that ends up being a bottleneck. We can multiply two polynomials, at least in principle. I mean, there are practicalities to this that make it more difficult, but let me say at least in principle. In time O of n log n. So just think about this here. So let me sort of pause here. I want to try to import, like sort of communicate how important this is. So if you can compute the discrete Fourier transform faster, so the upshot of it, because of some algebra that we're skipping, it's in section 9.4, but because of some algebra that we're skipping, if you can compute the discrete Fourier transform of a signal faster than O of n squared, say O of n log n, that means you get an exponential speed up in ordinary multiplication. At least in principle. I mean, sort of, there are all kinds of catches here. There's like a hidden constant here, right? So if that constant, remember, that's always the sort of hidden scam of these big O estimates. There's a hidden constant, and if that constant happens to be, say, the number of particles in the universe or the number of seconds in the expected lifespan of the universe, well, then okay, it's not that useful because the constant is too big. But it is but still, at least in principle and actually in practice. If you can speed up the discrete Fourier transform, then you can speed up multiplication, and that by God, that's like a moneymaker right there. If you can do multiplication faster than the next person, then you are made of wind. There's like you cannot. I mean, you can only sort of imagine what the breadth of the applications that go with that. You can write your own check. Actually, this is I think this is as of. So this is a real life algorithm. So in 2019, actually, just last year, which I know last year seems like 10 million years ago by now, but just last year, somebody actually found there exists an O of n log n algorithm for multiplying two capital N digit numbers. O of n log n algorithm for multiplying n digit numbers. That was a. I think that was a development that was expected for a long time, because exactly because of this fast Fourier transform thing that I'll talk about in the last 2 days of class. But somebody actually wrote down the details of an algorithm. And in fact, they're not quite as good as n log n, but there are actually fast algorithms for multiplying two numbers that are in use. So the motivating question for chapter 10 and 11. I mean, I guess it's the motivating question for chapter 11, and then chapter 11 is sort of at least my excuse for introducing groups, which is chapter 10. So the question that we look at for the rest of the course, sort of what is it that is driving us for the remaining week of the course, is how do we compute a discrete Fourier transform in O of n log n time? And the answer is a piece of, at least the way I like to look at it, is a piece of abstract math called group theory. Da, da, da. Groups. Okay. So anyway, yeah. So are there any questions about sort of, are there any questions before we go on and just start with groups? So then this will again sort of be starting from nothing, and so even if this discrete Fourier transform stuff was a lot of detail to absorb, and I think the best way to absorb that detail is to do problem set 10, to do those last two problems on problem set 10. Does everybody kind of see now that at least what I'm saying, that somehow if we can understand these abstract objects, which I call groups, then you can make a lot, in principle, you can make a lot of money by speeding up multiplication. So does that message kind of make sense? Yeah, say yes. Actually, while I'm waiting for everybody to catch up and absorb this, let me actually mention. So they actually mention a current open problem. Current open problem. If you can understand groups just a little bit better, you can find an algorithm for multiplying two n by n matrices in O of, I think it's O of n to the 2 plus a little bit. So basically you can get, so you can at least asymptotically, again, there are these sort of hidden constants always in, so I'm just totally going to mention this and not really explain this at all, but here the frontier of this actually particular area of mathematics is, if you can understand groups just a little bit better, and I actually don't, even though in principle I'm like like an expert in group theory or something. I like group theories. My research is in group theory. I don't actually know this problem off the top of my head. I sort of haven't quite absorbed the papers that go with it. But if we can just push our understanding of group theory a little bit, there's just one little problem to solve. Okay, it's not that little, but it's not an easy problem. But there's one problem to solve, and if you can do that, then you can basically write down an algorithm for multiplying square matrices in time that's just a little bit more than it takes to write down the matrices, right? Like an n by n matrix has capital N squared elements in it, and so the time it takes just to type in the question is O of n squared. And so if we can just push, as the human race goes, if we can just push our knowledge of group theory just a little bit more, then we can multiply matrices in sort of almost a constant multiple of the time it takes to write them down. Remarkable, amazing, or something like that. Okay, so anyway, I think let's just go ahead and plunge into group theory. All right, so groups. Okay, so I'm gonna, I guess, yeah, there's no way around it. I think we're just gonna plunge ahead and just lay down the definitions, and then, but then right away we'll go to an example, and it's an example we've actually talked about, even in this context to some extent, and so we won't be totally familiar. Okay, so what is a group? A group is a set G along with a binary operation, which we write as multiplication, such that the following axioms are satisfied. And so you may remember that if you write them all out, the axioms for a ring, remember we started off with sort of our first real large class of abstract objects that we looked at was rings. And in some sense, everything in the course up to now is basically ring theory. You want to look at this for, I mean, everything in the course is about making money through algebra, but the particular kind of algebra we're looking at is usually called ring theory. And so now we're doing something completely different. If you go back and look at the axioms of a ring, how many axioms are there? There's like 8 axioms for a ring, I think it is, maybe 9, depending on your formulation. There's 8 or 9 axioms for a group. There's only 3. Groups have to be associative. They need an identity, and so multiplication is associative. There's an identity element. There's an element which we call 1, and groups have inverses. So for every A, there's like a 1 over A. There's an A inverse. So that's it. There's only 3 axioms, and so and I guess it's always my feeling that if there's something that's somehow useful that has only 3 axioms to it, it's got to be pretty good. I mean, I guess I'm a group theorist, so I would say that, right? But okay, 3 axioms, not bad. And in fact, actually, if you go ahead and want to do the proof-oriented version of this class, which is Math 128A, which, fair warning, I am teaching next semester, so yay, you can come subject yourself to another semester of me in the fall, or boo. You might be in some position where you're forced to subject yourself to another semester of me in the fall. Sorry. Not sorry. Anyway, but 128A actually starts with, at least when I teach it, starts with groups, because in a way that the groups are simpler than rings. There's only 3 axioms as opposed to like 8 or 9 or whatever. That doesn't make them easier, actually, because there's a central assumption that we make that we're not going to make, that we're making here, which is that, see, abelian groups. So to have an abelian group means that multiplication is commutative. So abelian equals commutative multiplication, which is basically an assumption that we've made through. I think I may have hinted at the possibility of non-commutative multiplication, but okay, whatever. I mean, basically, every example we've looked at has commutative multiplication. And if you take Math 128A, that's the first thing you throw out, is that you actually generally start looking at a non-commutative example. Anyway, but for us, okay, we're dealing with abelian groups, and so what is the big example that we're looking at? If you have a finite field FQ, and remember FQs, remember the field with Q elements in it. Remember, Q has to be a prime power, like like 81 or 20 or 27 or 25, or usually for us 2 to the n. But if FQ is a finite field, it's a multiplicative group. Remember these, and remember the multiplicative group is the group of non-zero elements. The group is the group of non-zero elements. That is a finite abelian group, and let's review why. In red here, actually, let me make that in green. In green here, I'm going to sort of go review why is the multiplicative group of a finite field FQ times an abelian group. Well, it's associative. It's associative because multiplication in a field is associative. Actually, I should just write that Type it out. Multiplication in a field is associative. That's actually part of the axioms of a ring. Why is there an identity element in a field? Well, it's actually one of the axioms that every field has an identity element. And I guess the interesting thing that makes the multiplicative group of a field, of a finite field, a group is the inverse part. And remember there, in a field, I should have made this all green, huh? Oh well. Every non-zero element of a field has a multiplicative inverse, right? That's the definition of field. And so that's why that's three parts of why every the multiplicative group of a finite field, or actually of any field, is in fact a group. And then the last part is that multiplication in a field is also commutative. So that's the fourth. So just sort of collecting those reasons, that's the fourth reason why the multiplicative group of a finite field is in fact, as advertised, a group. So yeah, okay, well, we're looking at a brand new abstract idea, the idea of group. The air is kind of thin up there because there's only three axioms. You just need associativity, identity, and inverses. And so, like, well, how could you possibly do anything? Well, you'll see. I guess for us, we'll use a fourth axiom that groups are abelian. That we're only going to look at abelian groups where multiplication is commutative. And so there we go. So are there any questions about the definition of a group, or about the fact that the multiplicative group of a finite field is in fact really a finite abelian group, and so we are now justified in using the word group, which we're just sort of using that as like set or like bunch of stuff before. So any questions at this juncture? Okay, so we continue. All right, so okay, so there's the idea, there's the definition of group, and there's one important example of group that we have already seen. Okay, so let's look at subgroups. Yeah, so this is real abstract algebra kind of stuff. In abstract algebra, what is abstract algebra? So in abstract algebra, after we define a foo, we often next define a subfoo. Okay, so yeah, so this is what happens in a purely abstract class, abstract algebra class. Let's define subgroups. So if G is a group, a subgroup of G is a subset of G that is itself also a group, using the same operation as G. So in our notation, we write H is less than or equal to G, to indicate that H is a subgroup of some group G. And the reason we use the less than or equal to sign is we want to distinguish between H being a subgroup of G, where things are sort of closed, as we'll see in a minute, and H just being a subset of G, which is this notation. So, for example, if G is a group and A is an element of G, then bracket A, which you may vaguely remember, is the set of all powers of A positive, I hope this phrase jogs your memory, negative and 0 is a subgroup of G. It turns out that this is a subgroup of G we call the cyclic subgroup generated by A. So all right, so I claim that if I have just these powers of A, then that is actually itself a group. So how do we know that this is a subgroup? Actually, did I do an example of this? Oh, I forgot to do an example. Okay, so let me do an example. Well, I mean, you've actually seen examples of this. So let me do. So I will in a minute talk about why this is a subgroup. So then let me actually sort of break in here, interrupt myself, and do an example. And actually, let me do a particular example, which I hope is sort of aimed towards what's happening next. Okay, so let me insert an example here. So example. Actually, so example. Let G be the multiplicative group of the field of order 17, which is remember, F17 is just the integers mod 17. There's no sort of fancy stuff involving having to mod out by polynomials or whatever. So let's look at 4. The element 4, which is a non-zero element, mod 17, and I want to look at the cyclic subgroup generated by 4. I think we've done some of the, yeah, we've done some of these, but I want to remind you how this works. Well, that's the set of all powers of 4, 0, positive, and negative. Actually, because this is a finite group, we can just sort of do the non-negative powers. So 1 is a power of 4, 4 is a power of 4, 16 is a power of 4, which is the same thing as -1. Remember? So when I do this calculation, I'm going to sort of have in the back of my mind, well, 16 is -1. So if I again multiply by 4, I get -4, which is 13, and then or also known as -4, and then -4 times 4 is -16, which is 1, and so that we go back to the beginning. So anyway, so I just did that kind of quickly, and so if you remember. This is all done mod 17, and so yeah, and so I guess so. Let me sort of rewrite that as it doesn't matter in what order these come, because this is just a set of elements. So this set here, 1, 4, 13, 16, is a subgroup of multiplicative group of the field of order 17. So as it happens, that's not obvious, but I'll explain why that's true in a minute. So, so does that seem vaguely familiar? The multiplicative group, the cyclic subgroup generated by an element inside F17. So you may also remember that this the fact that we didn't hit everything means that 4 is not primitive. So there's an example of something of a non-primitive element. Okay, now in order to make sense of what happens next here, it's important to actually to be completely sure that that this thing bracket A actually is a subgroup of G. And so and so the way you do that is you apply the subgroup theorem, which is another one of these sort of closure things. So you may remember, I think we talked about the subspace theorem at some point. Subspaces are closed under vector addition and scalar multiplication, and we talked about the ideal theorem, which says that ideals are closed under addition and multiplication by elements of the outside ring R. And so this is yet another one of these kinds of theorems. So let G be a group and let S be a subset of G. So we're not assuming that S is a subgroup. Then S is actually a subgroup of G if and only if all 3 of the following conditions hold: identity, multiplicative closure, and inverse closure. So the first condition is the identity, that S has to contain the identity. The second condition is multiplicative closure, that if A and B are in S, then A times B is in S. And inverse closure, S is closed under taking inverses, that is, if A is in S, then A inverse is in S. So let's prove that that A is that bracket A is a subgroup of G. So suppose G is a group, and let little a be an element of big G. And again, we're going to define bracket A to be the set of all powers of A, positive, negative, and 0. And so let's check those three conditions. So the first condition is identity. Well, so why is the identity in bracket A? And so let's call this, and this is our capital S. So 1 is equal to A to the 0. So 1 equals A to the 0 is in S by the definition of S. Remember, S is the set of all powers of A, and one of which is A to the 0 of S. Okay, so good so far. Okay, so next. All right, we want a multiplicative closure. I wonder if I'll need another page. Well, maybe. So condition 2, we're going to check. We're going to assume. So how do you prove closure? So remember, this is always how you prove. This may seem vaguely familiar from the exam. How do you prove a closure thing? You assume that you have. How do you prove closure under multiplication? You assume you have two elements. Oops, I shouldn't call them A and B. Let me call them X and Y, because we already have something called A and it's fixed. So we assume we have two elements, X and Y, in S, and we want to conclude that X times, let me move this farther down. I'll give myself another page. X times Y is in S. All right, so so remember, that's how you prove a closure. That's how you verify or prove a closure condition. You assume the if part, and eventually you want to conclude the then part. I hope that seems familiar. So to say that X is an element of X means that X is equal to A to the N. And to say that Y is an element of S means that Y equals A, is an element of S means that Y is equal to A to the K for some N and integers N and K. Right, this is the definition of S. So again, I want to point out that this is the definition of S. That makes this work. Okay, so everybody good so far? Any questions so far? Okay, because in that case, then X times Y is equal to A to the N plus K, because the laws of exponents work for sort of elements of groups just as well as they do in other circumstances, which is an element of S, again, by definition of S. Remember, S is the set of all powers. S is the set of all powers of A, positive, negative, and 0. And whatever we don't actually know, we don't actually know what A to the N plus K is going to be, but it's a power of A, and so it's an element of S. And so is that okay so far? Yeah, I'm doing this because it's a homework problem. This is one of the problems in 11. It's something very much like this. Okay, one more. Let me finish up the last bit, and then I'll sort of show you the whole picture. So here's condition number 3. oops, fat fingers. Condition number 3, we want to assume that X is in S, and eventually we want to conclude that X inverse is in S. Subgroups need to be closed under taking inverses. Well, again, because X is an element of S, X is equal to a to the n for some integer little n. And so, again, X, which is equal to a to the n inverse, is equal to a to the minus n, where n minus n is, again, an integer. And so, again, by definition, of S, oops, why did that happen? By definition of S, X inverse is equal to an element of S. All right. So actually, so are there questions about that, or about this this procedure in general? Right. So there's step 1. Remember, so in order to verify or prove that something is a subgroup of a big group G, you want to check that something contains the identity. You want to check that's closed under multiplication. Under multiplication. And you want to show that's closed under taking inverses. And again, each of these closure verifications, each of these closure proofs has the same format. You always assume you have 2 things in your set, and you want to conclude that that their product is in the set. You want to assume you have something in the set. You want to conclude that its inverse is in the set. Always the same. All these closure proofs all work the same. Yeah, I hope I know this is not a proof class, but I do kind of hope that after taking this class, you'll have absorbed this general yoga of doing closure proofs. That's just generally how to do that. Anyway, so questions about subgroup proofs and this particular subgroup, proving that this particular subgroup is actually in fact a subgroup of G. Okay, so where were we? Oh, the Earth is blocking my view of Venus again. Okay, sorry. Having a little Marvin the Martian moment there. Okay, right. So this is important for us right now because actually, one of the things, at least to my way of thinking, that makes the Fourier transform work, and also the fast Fourier transform work, is looking at the Fourier transform, the fast Fourier transform, in terms of subgroups of the non-zero. Remember, it says what's C times C? It's the multiplicative group of non-zero multiplicative group of the non-zero complex numbers, which is in fact a group for the reasons that we sort of said before. Yeah, it's an abelian group because it has its multiplication is associative. It has an identity element, the element 1, and has inverses. Every non-zero complex number has an inverse in the complex numbers, and and multiplication is commutative, and so it's an abelian group. Anyway, so inside that big group, the non-zero complex numbers, we're going to define the group Cn to be the set of all nth roots of unity. In other words, it's all the complex numbers z, such that z to the n equals 1. So it is a fact that if omega is e to the 2 pi I over n, then Cn is actually all the powers of omega. Yeah, it's all the power. Yeah, well, I guess we have a name for that. This is the cyclic subgroup generated by omega. So for example, let me just draw my favorite example again. If little n equals 5, then we get the starfish. Right? This diagram here is actually the diagram of a group. I didn't quite do that right. Hang on. Try that again. There we go. Do some more carefully. Here, 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 here. That's better. Yeah, so for little n equals 5, this is omega squared, omega cubed, and omega to the 4th. Here's 1, which is omega to the 0. Anyway, so it is a fact. But so what I would like to do is show that by definition, when if n and k are natural numbers, are positive integers, then c sub n is a subgroup of the multiplicative group of the complex numbers, and if k divides n, then ck is a subgroup of cn. And so the proof of that is on problem set 11. I think this is the second to last problem that I'm going to ask you to do in the course. There's one more. Anyway, so the point is that this, besides being that, for other reasons besides the fact that it is equal to the cyclic subgroup generated by omega, is a subgroup of the complex, the multiplicative group of the complex numbers, and it's actually this. So the fast Fourier transform comes from the structure of the groups C sub n. So there. So I think we'll only sort of get to this, but it is the case. At least according to my understanding. If I have to say, if you asked a signals engineer, they might sort of say, "What is that guy talking about?" Here's what the fast Fourier transform is. They might have completely different and perhaps superior understanding. I will admit, because that's their business. And this is just I've never written any papers about this. I've thought about it anyway. Right. So so they will have some completely different understanding of the fast Fourier transform. But I think at least in terms of abstract algebra, the fast Fourier transform is a very strange little fact about the structure of the groups C sub n, as we shall see. Okay, so anyway, so that's why I want you guys to sort of get more familiar with these groups C sub n, is because that's you can I hope you can kind of see. Page up. Oh, page up works much better here instead of making that psychedelic thing. I hope you can kind of see that at least the discrete Fourier transform is already involving these groups C sub n in some way, except we're taking sums over them, but that's fine. But somehow the fast Fourier transform is going to be some clever idea involving the group theoretic structure of those groups C sub little n. Okay. Well, anyway, so that's going to be on problem set 11. So I guess, well, I don't want to spoil that for you. No, I want you guys to go through that yourself, because that's really the way you learn. And so let me actually then turn to another subject, which is actually just sort of cleaning up some stuff that we talked about in terms of fields. Let's talk about orders of elements. So let G be a group and let A be an element of G. So if A to the n equals 1 for some positive integer n, we define the order of A to be the smallest such n, the smallest possible little n, such that A to the n equals 1. Otherwise, if no positive power of A is equal to 1, then we say that A has infinite order. And so, for example, if we let omega be e to 2 pi I over capital N, and I somehow cannot resist drawing the same. Okay, I'll draw a different picture just to make it a little bit different. Let me draw capital N equals 6. And so here's this is actually a little easier to draw too, so that's convenient. All right, so this is dividing up. This divides up the unit circle into. So here's omega for capital N equals 6. This is omega squared. Omega cubed is equal to -1. omega to the fourth, omega to the fifth. This is 1. Here we go. So there's the powers of omega. For n equals 6, there's the powers of omega in the complex plane. Oh yeah. So for this, we see from this wagon wheel picture or similar wagon wheel pictures for other values of capital N, that omega and omega squared, if you look at all the powers of omega going up to capital N minus 1, those are all not equal to 1, right? Because you, and for the simple reason, not simple, for the reason that if you take a power of omega that doesn't quite go up to capital N, then you're not done going all the way around. Oh gosh, am I going to go the right way around here? Go all the way around the unit circle. I think that's the right direction. Right. I'm not an aerobics. So can somebody tell me, is this counterclockwise? It's supposed to be counterclockwise. No, that was clockwise. So this is going to be counterclockwise. There we go. So this is counterclockwise because it's going to look like clockwise for me. Anyway, so yeah, so because omega is not done going all the way around the circle, if you take powers 1 through powers 1, try that again, powers 1 through capital N minus 1, you don't get 1, but omega to the capital N is equal to 1. Well, and so that's e to the 2 pi I over n taken to the nth power, and that's equal to e to the 2 pi I. That is equal to 1 because when you go all the way around the unit circle, you get you start over here at the positive x-axis and go all the way around the unit circle. You get back to the beginning, 2 pi. So the order of omega is capital N. All right, and so does that make sense? That example makes sense? I think I should actually erase that, make it better at capital N here. So are there any questions about that example of the order of an element? Okay, so so let's look at right. Oh yes, and that I think that's another problem. All right, so so let G be a group and let A be an element of capital G, finite order little n. Then if I take A to some power k, that only depends on what k is mod little n. And so so sort of actually let me remind you of an example of this. If alpha, sorry, example, if alpha is primitive, a primitive element in F512, the order of alpha is 511. Remember, because the order of a primitive element is 1 less than the number of elements in that finite field. So when you look at alpha to the k, that only uses the value of k mod 511. This is what that's what this theorem is saying, is that so if you have an element of order, if you have some element of order 511 and you look at its powers, then the only thing that really matters for those powers is what that exponent is mod 511. And so that, remember that when we do that doubling when we do that squaring exercise, those Frobenius orbits, that's why all the time you have to take those exponents mod 511 and not mod 512. Anyway, so so the point is, if k equals L, k equals L in mod n, if and only if a to the k equals a to the L. And so here's a proof. So if we assume, oops, if we assume that k equals L mod n, then as we saw a very long time ago, k is going to be equal to L plus qn for some integer q. Very long time ago, months now, which, you know, thanks to the quarantine, must seem like decades ago. Okay, so at some point we did that. So in that case, a to the k is equal to a to the L plus qn, which is equal to a to the L times a to the qn, because the laws of exponents still work here, which is equal to a to the L times a to the n to the q, again, thanks to the laws of exponents. And now we recall that because the order of k is n, we're assuming that that k has order n. There we go. And so because of that, a to the n is equal to 1. I mean, it's also the least element such that that the a to the n equals 1, but still. Anyway, so this is equal to a to the L times 1 to the q, which is a to the L. So on the one hand, if k is equal to L mod n, then a to the k is equal to a to the L. My daughter came up. She says, "On the one hand, yes. On the one hand, on the other hand." All right. So so we're done. So that part's done. That's our conclusion that we wanted to reach. And on the other hand, suppose a to the k equals a to the L. Well, that means that a to the k minus L, oops, that means that a to the k minus L, a little shorter here, is equal to 1 by the laws of exponents in the usual way. And so, so now, so, oh my God, here's a throwback. Ready? By the division algorithm. What? The division algorithm theorem. I think we call it the division theorem. By the division theorem, we know that, oh my God, what does that say? That says that when you divide k minus L by n, you get some quotient and some remainder, where the remainder is strictly greater than 0 and is strictly less than n. So R is equal to k minus L minus qn, and a to the R is equal to a to the k minus L minus qn, which is equal to a to the k minus L times a to the minus qn, which for reasons similar to the other half is equal to 1 times 1 equals 1. I ran out of space here, but that's fine. So whoa, I didn't want to do that. What the heck happened here? Undo. There we go. Okay, so page width. There we go. That was weird. Let's try that again. There we go. So what? It's been a long semester, huh, friends? All right. So so it is the case that a to the R is equal to 1. Oops, is equal to 1, and R is a non-negative integer less than n, but we know, but n is the smallest positive integer power of a that is equal to 1. Well, that means that r can't be positive, so r equals 0. In other words, what does it tell us? So k minus l equals qn, i.e. K is equal to L plus Qn, which means that K is equal to L mod N. All right, so no, sorry. Despite my inability to make the pages work correctly, I think that worked out okay. All right. So in other words, yeah. So again, if you have an element, here's the upshot again. Even though again, you don't need to sort of know the proof. If A is an element of order little n, then a to the k depends exactly on what the value of k mod n and nothing else. So any questions on that? Oh yeah. Oh my gosh. Sorry, Ishan, you asked a long time ago. You have e to 2 pi I equals 1. That is correct. It's e to 2 pi I equals 1. Because sorry, let me go back and answer that now very old question. My bad. So if I go back, oh yeah, over here, why is e to 2 pi I equal 1? Because remember, that was because e to the I theta corresponds to the angle. Let me blow this up again. Remember, e to the I theta corresponds to. I think maybe I'll just answer this question, and then we'll pick up where this left off later. So yeah, e to the I theta corresponds to the position of the unit circle corresponding to the angle theta. Yeah, and 2 pi has the same position as the angle 0. That's right. Okay, so no, I have 2 minutes. Dang it, I have 2 minutes. I'm going to keep going. Let's see. I'll just talk about one more thing. All right. So, but for now, are there any questions about how exponents are taken? The exponents on an element. The exponents on an element of order n are taken mod n. So, okay. All right. Okay, so let's. Oh yeah. Oh my goodness. This is. There we go. Yes. So this is again a thing that we mentioned before. So let A be a group and let A be an element of finite order little n. And the cyclic subgroup contains n elements. Well, it contains elements, has order n. So and why is that? Well, the point is that the elements. Let me sort of make this bigger again. Of bracket A are in bijection with correspond with the possible values of a to the k. And those correspond with the possible values of k mod little n. Remember, we just saw that the only thing that matters when you take powers of an element of order n is what those exponents are mod n. And so there will be exactly n of those. So that's exactly a to the 0, which is 1, a to the 1, a squared, all the way up to a to the n minus 1, and there are n things. So that really just follows from what we were just talking about. And it is also a case that if G is capital G is a group and little a is an element of capital G of finite order little n, then the order, oh yeah, I hope this sounds vaguely familiar, then the order of a to the little k is n over the GCD of k and n, and that I will leave to you in problem set 11. All right, we're 1 minute over, and so now we're going to get to the big idea. This is, and it's not going to look like it. This is the big deal. Because the weird thing is that the fast Fourier transform, one of the 10 greatest algorithms of the 20th century, boils down to, at least to an algebraist, boils down to a strange fact. Yeah, it's like on the internet they said like this one weird trick. Well, there's one weird trick. There's this one weird fact about cosets. This abstract idea that I'm about to describe you, I'll get to next time about called cosets. This one weird fact about cosets allows you to multiply integers and matrices and all kinds of stuff faster than you have any right to doing. All right, but why that is, we'll get to next time. For now, thanks for your patience and your time, and